Hello everyone, I am Assistant Professor Milan V. Patel. I am an Electrical Power System from the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Today we will discuss chapter number 6, Power Factor, from the subject Power Quality and Management, having a subject code 2180911 of the BE Semester 8 Electrical Engineering Department. So today we will discuss chapter number 6, power factor. So first of all, what is power factor? So power factor is nothing but it is a cosine angle between the voltage and current. And another definition of the power factor is R by Z, means resistance divided by impedance. And the last definition for the power factor is that in form of powers. So power factor is given by P by S, active power divided by apparent power S. So first of all, introduction. So power factor is important in power quality discussion because due to the low power factor, equipment may fail the cost equipment may fail and the cost of the power may increases, so increasing in the generator of the meeting the demand. So there are main 2 points considering for the power factor. First one is the damage or equipment's failure. Second one is the increasing in the cost for the power generation power generation. So now next topic is active and reactive power. Active and reactive power. So we know that the apparent power S can be determined by S is equal to VI. S is equal to VI, where V is the voltage and I is the applied current. This is the equation for apparent power for single phase. S is equal to root 3 VI. So this is the equation for the three phase power, three phase apparent power. Now active power can be defined by P is equal to VI cos phi. P is equal to VI cos phi for the single phase and P is equal to root 3 VI cos phi for the three phase. So power factor may be viewed as the percentage of the total apparent power that is converted to the real or useful power. So if the power factor is 0.8, it means 80% of the apparent power S is converted to useful work. Okay, so 0.8 power factor means only 80% of the power from the apparent power will be used for the useful work, will be converted into the useful work. So power factor cannot reach 100% due to the L and C of the circuit. L and C means the inductor and the capacitor of the circuit. So power factor never become 100% or 1. So the active power is portion of the apparent power that prevents it from obtaining a power factor 100%, and the power that an AC electrical system requires in order to perform useful work in the system, that is active power. Now reactive power. Now reactive power. So reactive power sets up a magnetic field in a transformer core, allowing transformer of a power from primary to secondary winding. So reactive power is useful to set up the magnetic field in a transformer core, allowing the transformer to transform the energy from the primary to the secondary winding. And in the motor, so that torque is produced. So reactive power is useful in transformer for setting up the magnetic field, and also it is useful in the motor to setting up the magnetic field, and due to this magnetic field the torque will produce. So S is given by under root p square plus q square. This is the power triangle. This is the power triangle. This is active power, this is reactive power, this is apparent power, and this is the power factor angle phi. So from this figure we can derive this four equation, which is S is equal to under root p square plus q square, where p is active power, q is reactive power. Now p is given by S cos phi from this figure, and q is equal to S sin phi from this figure, and q by p is given by tan phi. Q by p is tan phi, where the phi is the power factor angle, where phi is the power factor angle. So now if the XL is the inductive reactance given by, so this is the figure, this is the applied voltage V, this is the resistance R, this is the inductance L, and this is the current due to this voltage applied. So XL is given by 2 pi FL. We know that the value of inductive reactance is given by 2 pi FL. So Z is equal to R plus JXL. R plus JXL. So reactive term is in multiple with the J, immediate term J, where J is equal to under root minus 1 and phi is equal to tan inverse XL by R. Phi is equal to tan inverse XL by R. So this is the power factor angle. Now this is the waveform for the applied voltage. This is the applied voltage. This is the applied voltage V, and this is the current producing due this applied voltage, and this is the phi. This is the phi phase displacement due to this inductive effect. Due to this inductive effect. So this is the inductive circuit for the power factor. Now example, what is the power factor of a resistive or inductive circuit characterized by the R is equal to 2 ohm and L is equal to 2 millihenry and the frequency is equal to 60 hertz. So we know the equation of the XL is given by, the equation of XL is given by 2 pi FL. So put the value of 2 pi f is equal to 60, L is equal to 2 millihenry, means 2 into 10 raised to minus 3. So this answer for the inductive reactance is given by 0.754 ohm. 0.754 ohm. Now tan phi is equal to XL by R. So XL is equal to 0.754 and R is equal to 2. So 0.754 divided by 2 is equal to 0.377. 0.377. So phi is equal to 20.66 degree. Phi is equal to 20.66 degree. From that power factor angle, we can simply calculate the power factor by putting the value in the power factor is equal to cos phi. So cos 20.66 is equal to 0.936 lagging. 0.936 lagging. This is lagging because here inductive value inductance is given. Suppose here capacitor is there, then this value is in leading. So now next example, what is the power factor of resistance capacitance circuit when the R is equal to 10 ohms, C is equal to 100 microfarad and the frequency F is equal to 60 hertz. So now we know the equation of the capacitive reactance. Capacitive reactance Xc is equal to 1 upon 2 pi Fc. So put this value of the F and C in this equation, we will get the 1 upon 2 pi multiply by 60 frequency multiply by 100 microfarad, means 10 raised to minus 6. So by solving this equation we will get the answer of the capacitive reactance is 26 26.54 ohm. So this is the capacitive reactance obtained from the given data. Now tan phi. Tan phi is given by Xc by R. Xc by R. So it is given by 26.54 divided by 10 divided by 10. So the answer for the tan phi is equal to 2.654. From this equation we will get the value for phi is equal to 69.35 degree. 69.35 degree. Now put the value of phi in the equation of the power factor. Cos phi is equal to cos 69.35 is equal to 0.353 leading. 0.353 leading. So this is the leading power factor due to the capacitance present. Okay, I hope you understood these two examples of the power factor. Now consider an inductive circuit where application of voltage produces the current I as shown in the figure. So the current I is again divided into the active and reactive component IP and IQ. IP and IQ, where IP is the active power component, current's active power component, and IQ is the current's reactive power component. So from this is the figure, this is the figure in which this is the actual power Q, this is the power factor angle phi, this is the active component of the current, and this is the reactive component of the current. Active component is given by I cos phi and reactive component is given by I sin phi. So from this figure we can derive the equation Ip is equal to I cos phi and Iq is equal to I sin phi. So simply from this equation we can write the equation for the power. Active power P is equal to Vi cos phi and reactive power Q is equal to Vi sin phi. So S is equal to under root P square plus Q square. Put the value of P and Q from above equation in this value in this equation. So we will get under root Vi cos phi square plus Vi sin phi square. So again simplified this equation by v square under root v square I square cos square phi plus v square I square sin square phi. So take v square I square common out from these two terms. So it will vi out of this under root. So in square root cos square phi plus sin square phi is there, and we know the value of the cos square plus sin square is equal to 1. So simply put the value of this term 1. So our answer for S will be Vi. This is the simply derivation of the apparent power S is equal to Vi. Now this is the simple diagram for the phasor diagram for the system. So this is the actual current I, this is the active component of the current, this is the reactive component of the current, this is the power factor angle phi. Now simple, this is the applied voltage V, this is the applied voltage V in phasor form, this is the active power P, active power P, this is the reactive power Q, and this is the summation, phasor summation of this active and reactive power S. So this is the power phasor, this is the power phasor. Now theoretical limits of the current, theoretical limits of the current, this is the inductive current, this is the capacitive current, and this is the applied voltage V, applied voltage V. So in this above region, this is in the this above shaded region, current is leading to the applied voltage, and below region current I lags to the voltage. So this is the lagging current and this is the leading current with respect to this applied voltage. Now next topic is displacement and true power factor. Displacement and true power factor. Now displacement is the angle between fundamental voltage and current. So it is the angle between fundamental voltage and current. So fundamental waveforms are pure sinusoidal, but due to the harmonic distortion, the power factor angle may be differ by the actual fundamental wave. So true power factor is given by total active power P, divided by total apparent power S. So true power factor is given by P by S, where P is the total active power and S is the total apparent power. So utility pendings are based on the true power factor of the facility. So now next topic is power factor improvement. And so in power factor improvement, main two ways are there. So for power factor improvement, main two methods are there or two ways are there. First one is to reduce the lagging reactive current demand of the loads. So this is the lagging reactive demand. IQ is the total lagging reactive demand of the load. So simply adding capacitive current in opposition of the IQ, we will decrease the value of the lagging reactive current. So first method is by applying the leading capacitive current. So due to this, we will reduce the reactive current component, and from this we will get the value, we will reduce the value of the reactive current, and by this we will minimize the power factor angle, and from this we will get the higher or improved power factor. So now compensate for the lagging reactive current by supplying leading reactive current. So this is the reduced lagging reactive current demand and compensate for the lagging reactive current by supplying the leading reactive current. So now lagging reactive current demand may not be totally eliminated but may be reduced by using power system devices or components designed to operate with low reactive power. Practically no devices in a power system require leading reactive current to function. Therefore, in order to produce leading current, certain devices must be inserted in the power system. So these devices are referred to the power factor correcting equipment. So there is no devices in the power system which will generate leading kVAR or leading current. So we have to provide extra equipment for the power factor correction. For the power factor correction.